All right, we are starting into Unit 3 on intermolecular forces and properties of substances. This unit centers around how chemicals interact with each other and with themselves, and really explores all aspects of solids, liquids, and gases. So you'll notice that we're starting with topic 3. I kind of restructure and reorder things. We're going to start with this one, just exploring the really basics of solids, liquids, and gases, and then we will get into what's called intermolecular forces, which is what holds substances together, and then start getting into more about solids, and then we'll go into more about liquids, and then we'll end the unit with all the information about gases. So, kinetic molecular theory is really the theory that governs everything we're going to look at in this unit, and explains the different states of matter. So first, gas molecules have tiny volumes compared to the volume of the space that they occupy. So there's a picture of that up here. If these are our tiny gas particles and this is the container they're in, if you squish them together, they only take up a very small fraction of the total volume. We also say that they're so small in reality. I mean, these particles are giant compared to what the actual gas particles would look like, that they are so small that their volume is considered negligible. That means we can ignore it. It doesn't really have much volume. So when we look at the volume of a container of gas, we just say the gas volume is the container volume. They're equal. Gases are all separated by large distances, so they're mostly made of empty space, and they have low density. What that allows gases to do is be compressible. So if we can take a gas and compress it into a smaller area, it makes it compressible. Or if we can take a substance and do that, it is compressible. Gases are highly compressible, whereas solids and liquids aren't. Gases also are in constant random motion. So if we could really have a picture of a gas, all these particles will be moving around very fast. They continually collide with one another and their container walls. Liquids have a definite volume as the particles are close together, but can still slide past one another. Liquids assume the shape of their container, and they have higher densities than gases because they're more compact. Lastly, solids have a definite shape and a definite volume. So we can we can actually measure with a ruler the shape and volume of a solid, where we can't do that with liquid or gas. The particles are packed together. Some are crystalline in structure, which means they're highly organized. Others are what we call amorphous, where they're more kind of squishy, more like think Play-Doh. That is an amorphous solid, right? Can have a random shape to it. Solids tend to have the highest densities as they have the atoms more closely packed together because of that structure of them. So the density of the states of matter relates to how closely packed together the particles are to one another. So gases have less particles per area or per volume, so they have the lowest density. Your particles of gases are more spread out, or the most spread out. Liquids are going to be more packed together, and that increases their density, and they can slide past each other. And then solids are the most packed together. And we organize them to get the highest density for those. All right, we're going to explore the states of matter here a little bit. So we're going to start with just this neon. We've got a solid neon pictured here. You can see that the particles are clumped together. They have motion to them. They have movement. They're vibrating, but they're not sliding past each other. They're more locked in place. They have a shape to them, right? We could even measure the shape around this. If we look at a liquid, we can see that the particles can now have more freedom to move. They slide past each other, they bump into each other a little more, and they have a little more activity to them. The particles are moving faster. Now you'll notice that we just had one particle escape That is evaporation. So when they get enough energy by bumping into each other that they can actually leave the surface, we call that evaporation. If we add a little more heat to it, more of them will evaporate. If we were to cool it down, less of them would evaporate or more would condense. And then if we look at the gaseous form, the particles are moving all over the container. The liquid, they stick to the bottom of the container, really, right? If we pour water in a glass, it's going to be at the bottom of the glass. We get that liquid. So for a gas, it's going to fill the container. So whatever the container's volume is the volume of the gas. The particles move around. They bump around randomly. They bump into each other, the walls of the container, all of that stuff. If you pick a particle and watch its motion, it's kind of random, but it moves until it comes in contact with something. You can also see that the particles, sometimes they get close enough that it seems like they're trying to stick to each other. Especially ones that are a little slower, they seem to have some attraction, like these ones here, right? They've got a little bit of attraction. So that can happen as particles slow down. They get more attractions. If we were to cool this, slow down the particles, you're going to start to see that they get more attractions between them. They start to stick in little groups. So that's condensing. If we heat it, we are separating, giving them more energy, so they're more likely to not stick to each other because they have enough energy when they bump into each other to separate and just bounce off. Let's take a look at water. Water is a solid. You can see those little vibrating water molecules there. As you cool it, you get this really kind of more rigid structure. You can see there's these gaps, though, between the water molecules. So the way that they're attracted to each other, we call it hydrogen bonding. We're going to be looking at that later in this unit. But it gives them kind of this odd structure to them. As we change it to a liquid, you can see that they actually get to be closer to each other, which is rare. Most solids are more dense than liquids, but water's kind of a special one because of that, the attractions between them. Again, you can see the water is all contained at the bottom of the container. The particles are sliding past, bumping into each other. They have more motion. And then as a gas, we get those particles moving all around, spinning, bumping into each other, all of that. So we get that more constant random motion. You can see they start to try and attract to each other. Those attractions are much stronger than what the neon had. So it's more likely for them to attract. So they would need higher temperature in order for them not to attract, which is why it takes so much energy for water to turn into a gas. You got to break up all those attractions. So that's a little bit of exploring on our states of matter. So finally, just some conclusions. Solids, below a certain temperature, the molecules are locked in place due to having strong attractions between them. And that creates a solid. It's going to have more of a rigid structure to it. A liquid, the particles moving, they're moving too fast for the molecules' attractions to hold them in place. Some molecules are bumped out at the surface. We get evaporation there. But those particles are moving, sliding past each other, but they are staying at the bottom of the container. And then a gas above a certain temperature, the molecules are spread out and attractions are insignificant. They bounce off the container walls and push on it. We call that pressure. We're going to explore lots about pressure in this unit. And then the particles travel in a straight line until they hit another particle or the container. So the type of question that might be asked about different states of matter is something like this. We have a box that below represents a closed container with liquid ammonia and H3 molecules. In the box on the right represent the same sample of ammonia after undergoing complete evaporation. So as a liquid, we can see the particles are more touching each other. They're at the bottom of the container. If we want to create a gas, then we need to separate them from each other. Now, the key is that we want to separate and still make it ammonia. It doesn't indicate that it's undergoing a reaction. It's just evaporating. So we should have the same molecules just spread out. And that is a type of question that might be asked with this. The other types of questions as we look through this unit is they're going to ask us, well, what type of force is holding the liquid particles together? What kind of attractions are those? All of that type of thing. So that's really what we're getting into. And then as we continue through the unit, when we get to the gas part at the end of the unit, we're going to look at, well, what kind of pressure do those gas particles create? What's their temperature? What's the amount of gas? How do we measure that? What is the difference between an ideal gas and a real gas in the real world? So those are the types of things we're going to explore in this unit. Thanks, guys.